In this video, we're going to discuss how implications are used in mathematics and logic. So first, let's recall that a logical statement is a declarative sentence that is unambiguously either true or false. So for example, here are some examples of logical statements. 5 is an integer is a true statement. -5 is not a rational number. That's false. It is a rational number. 2 is less than or equal to 5. That's true. 2 cubed is equal to 5. No, it's not. It's equal to 8. You might want to check this one for yourself. Pi to the e is less than e to the pi. It might not be clear to you if it's true or false, but it's an unambiguous statement and it happens to be true. 11 is even. That's false. And square root of 2 is an element of the rationals. We know that's false. Square root of 2 is irrational. So these are all logical statements in the sense that they are all declarative sentences that are unambiguously true or false. So in logic, there are four main connectives. They are not, also called negation. There's and, or conjunction. There's or disjunction. And there's implication. In this lecture, we're going to discuss implication, also known as if-then statements. So let's let P and Q be logical statements. Then the statement if P then Q is the logical statement that is true when either P and Q are true or when P is false. So in particular, it's false only when P is true and Q is false. We also write if P then Q as P implies Q, where implies is represented by that sort of double arrow. So here's the truth table for P implies Q that's reflected in the definition above. So if P and Q are both true, then P implies Q is true. If P is true and Q is false, then P implies Q is false. If P is false, whether or not Q is true or false, so if P is false and Q is true, then P implies Q is true. And if P and Q are both false, then P implies Q is true. So this truth table can be a little bit hard to get used to, but it is the standard truth table for implications in classical logic. And to get some familiarity with it, or a little bit more comfort with it, let's just practice. Another way to think about P implies Q and the truth table for P implies Q is to notice that it's logically equivalent to not P or Q. So if we look at the truth table for P implies Q, we can see that we have the truth table that we wrote before, and if we compare that to the truth table for not P or Q, you can see that when P and Q are both true, then both P implies Q and not P or Q are true. If P is true and Q is false, then both P implies Q and not P or Q are false. If P is false, regardless of the truth value of Q, then not P or Q is true. Also, P implies Q is true. So you can see that these statements are logically equivalent. And sometimes we take not P or Q as the definition of P implies Q. And that helps to kind of give a little bit of a background explanation to why the truth table for P implies Q is as it is. But again, it can be a little bit hard to get used to, so let's look at some examples. And the strangest examples, the examples where you have to just apply the truth table, are ones where the statements don't seem to be related. So for example, let's consider this statement. If -5 is not a rational number, then 5 is an integer. Okay? Well, this is a strange sounding statement. And you know, in ordinary language, it probably wouldn't be clear whether to call it true or false. But in logic, this is a well-formed statement, and so we can apply our logical rules for deciding whether an implication is true or false. So we can view this as a statement of the form if P then Q, where P is the statement -5 is not a rational number, and Q is the statement 5 is an integer. Okay, P is false and Q is true. So according to our truth table for P implies Q, it follows that P implies Q here is true. That is, the statement if -5 is not a rational number, then 5 is an integer. That's a true statement. Now let's consider the statement if 5 is an integer, then negative 5 is not a rational number. Again, a strange sounding statement. Okay, and it might not be clear whether to call it true or false. But again, we can apply our logical rules for deciding whether an implication is true or false. Again, we can look at this as a statement of the form if p then q. So p is the statement 5 is an integer, and q is the statement negative 5 is not a rational number. Here p is true, but q is false. And so according to our truth table, p implies q here is false. So we'd call this statement, if 5 is an integer, then negative 5 is not a rational number. That's a false statement. What about this one? So now, if 2 is less than or equal to 5, then pi to the e is less than e to the pi. Okay, again, kind of strange sounding statement. Not clear what the relationship is between the hypothesis and the conclusion. So it wouldn't be clear in ordinary language whether to call it true or false. But as before, we can apply our logical rules. We look at this as a statement of the form if p then q, where p is the statement 2 is less than or equal to 5, and q is the statement pi to the e is less than e to the pi. Okay, p is true, and q is true, so it follows that p implies q is a true statement. So we would say that this statement, if 2 is less than or equal to 5, then pi to the e is less than e to the pi, is a true statement. Then one last example, let's consider this statement. If 11 is even, then square root of 2 is a rational number. Well, it's a strange sounding statement. Okay, in this case, when we apply our logical rules, we'll notice that we have 11 is even as the hypothesis, p, and root 2 is a rational number as the conclusion, q, in the if p then q form. Those are both false statements, and so according to our truth table, we call p implies q true. Okay, so the statement if 11 is even, then square root of 2 is a rational number, we would say that that's a true statement. Okay, closely related to implications are biconditionals. So if p and q are logical statements, then the statement p if and only if q is the logical statement p implies q and q implies p. So we'll denote p if and only if q as here you can see the double arrow between p and q, so we read that as p if and only if q, or as p iff q. So either one, the double arrow or the iff, both mean if and only if, and we refer to such a statement as a biconditional. Okay, so the truth table for a biconditional shows that the biconditional p if and only if q is true exactly when p and q have the same truth values. So when p is true and q is true, p if and only if q is true. When p is false and q is false, p if and only if q is true. If they have different truth values, if p is true and q is false, or p is false and q is true, then the biconditional is false. Okay, and so it kind of makes sense given that when we say when p and if and only if q is true, we call p and q equivalent statements. Okay, but meaning they both have the same truth value always. So let's consider the logical statement p implies q. We're going to lay down some notation or definitions regarding p implies q. So we'll call p the hypothesis or the antecedent of the statement. Call q the conclusion or the consequent of the statement. When p implies q is true, we say that p is sufficient for q. Okay, so p is a sufficient condition for q. And when p implies q is true, we'll also say that q is a necessary condition for p. All right, so that's all terminology that's fairly common that you're likely to see again. Some statements closely related to p implies q are the following. The statement q implies p is called the converse of p implies q. The statement not p implies not q is called the inverse of p implies q. And the statement not Q implies not P is called the contrapositive of P implies Q. So what's important about these related statements is which ones you can prove that count as a proof of the others. So which of these are logically equivalent to the others. All right, and so that's covered in a theorem that we're going to state. But before we do that, let's get used to forming the various related statements of an if-then statement. So let's consider the statement, if m is divisible by 4, then m is divisible by 2. Okay, if m is divisible by 4, then m is divisible by 2. If you think about it for a minute, you clearly see that that's a true statement. If we write it as if P then Q, or P implies Q, then P would be the statement m is divisible by 4, and Q would be the statement m is divisible by 2. The converse then, Q implies P, would be if m is divisible by 2, then m is divisible by 4. The inverse is if not P implies not Q, so that would be if m is not divisible by 4, then m is not divisible by 2. And the contrapositive, not Q implies not P, is if m is not divisible by 2, then m is not divisible by 4. So if we look at this and think about which ones are true or false here, we can see that the original statement, P implies Q, is true. Okay, so if m is divisible by 4, then it is in fact divisible by 2. And the contrapositive we can see is true, the last one there. If m is not divisible by 2, then it's certainly not divisible by 4. However, here the converse and the inverse are both false statements. So if m is divisible by 2, m may not be divisible by 4. So for example, 2 and 6. And the inverse, if m is not divisible by 4, then m is not divisible by 2. Again, the numbers 2 and 6 show that that inverse statement is also false. So what about this statement? If m squared is even, then m is even. Okay, so we can write that as of P implies Q, where P is the statement m squared is even, and Q is the statement m is even. The converse is the statement if m is even, then m squared is even. The inverse, not P implies not Q, is the statement if m squared is not even, then m is not even. And the contrapositive is not Q implies not P, and here that's if m is not even, then m squared is not even. Okay, and again, if we think about whether or not these statements are true or false, if m squared is even, then m is even. The original statement is true, and so is the contrapositive. If m is not even, so if m is odd, then m squared is not even. M squared would also turn out to be odd there. And here, unlike in the previous example, the converse and the inverse are also both true. So if m is even, then m squared is even. That's true. And if m squared is not even, so if m squared is odd, then m is not even, then m is odd. That's also true. Okay. So you can see that the kind of pattern we observed is that the original statement and the contrapositive were both true in both cases. The converse and the inverse, in one case they were both true, and in the other case they were both false. Okay, so you can see there might be some kind of relationship here, and indeed there is. Let's consider the statement P implies Q, the logical statement P implies Q. Then we have this theorem. The statement and its contrapositive, those statements are logically equivalent. The converse and the inverse are also logically equivalent. However, the statement and its converse have no logical relation, and therefore also the contrapositive and the converse have no logical relation. And the negation of the statement is often confused with the inverse of the statement, but the negation and the inverse also have no logical relation. So we'll see that, we'll prove that, and we'll see it by looking at the truth tables for the various statements. So recall the truth table for P implies Q. And now let's look at the truth table for the contrapositive, not Q implies not P. Okay, so we can see if P is true and Q is true, then not P is false and not P is false. And so not Q implies not P is going to be true. Okay, so when P is true and Q is true, the contrapositive is true, as is P implies Q. If P is true and Q is false, not Q is true, not P is false. So the contrapositive is false, not Q implies not P is false, as is the original statement. If P is true and Q is false, P implies Q is false. Okay. Now what about if P is false and Q is true? Then not Q is false and not P is true, so not Q implies not P, that's true, as is P implies Q. And if P and Q are both false, not Q and not P are both true, and not Q implies not P turns out to be true. So you can see that under exactly the same inputs of truth values for P and Q, you get exactly the same output of truth values for P implies Q and the contrapositive not Q implies not P. So that's what we mean when we say they're logically equivalent, is those two statements, P implies Q and the contrapositive, always have the same truth values as each other. Okay. You can see that with regard to the converse and the inverse as well. And really, the reason for this is that the inverse is the contrapositive of the converse. So if you think about that for a second, you'll see that it's true. And if you look here at the truth tables for the converse and the inverse, you can again see that they're logically equivalent statements. So if P and Q are both true, the converse and the inverse are both true. If P is true and Q is false, the converse and the inverse are both true. If P is false and Q is true, then the converse and the inverse are both false. And if P is false and Q is false, then the converse and the inverse are both true. So again, they're logically equivalent. Okay, so now when we say that statements have no logical relation, then what we mean is that they don't always have identical truth values. And so you can see that if you look at the statement P implies Q and its converse, Q implies P, you can see that those truth tables, they sometimes give different outputs given the same inputs. So they're both true if P and Q are both true, or if P and Q are both false, then the converse and the inverse are both true. But you can see there, if P is true and Q is false, the statement is false, but the converse is true. If P is false and Q is true, the statement P implies Q is true, but the converse, Q implies P, is false. Okay, so we would say that those have no logical relation. You don't know if the original statement is true, you don't know if the converse is true. Okay, what about the negation of the statement and the inverse? So these are two that are often confused. The negation of P implies Q is not the same as the inverse. They have no logical relation. So you can see here the truth table for the negation of P implies Q. So first we have the truth table for P implies Q, and then we just negate that truth value. And if you look at the truth value for the inverse, or the truth table for the inverse of the statement, then you can see that they don't always give the same truth values. So if P and Q are both true, the negation of P implies Q is false, but the inverse of P implies Q is true. If P is true and Q is false, the negation of P implies Q is true, and the inverse is true. If P is false and Q is true, the negation is false, as is the inverse, but then another difference, if P is false and Q is false, the negation of P implies Q is false, but the inverse of the statement is true. So we would say again, those have no logical relation to each other. Okay, and one important takeaway about this is that a common and valid proof technique is proof by contrapositive. So, since P implies Q is logically equivalent to not Q implies not P, then if you need to prove P implies Q, you can prove the contrapositive not Q implies not P, and that'll suffice for a proof of P implies Q. All right, so you should always consider doing that. So for example, if you're asked to prove if m squared is even, then m is even, then you might consider proving the contrapositive if m is not even, then m squared is not even. It might be, and indeed in this case it is, easier to prove the contrapositive than to prove the original statement. And so you might as well do that. However, an important warning, if you're asked to prove P implies Q, definitely do not try to prove the converse or the inverse of the statement, because those are not valid. Those are common mistakes. People try to prove the converse instead of the original statement, or they'll mistake the inverse for the contrapositive and try to prove the inverse. Don't make that mistake. Be very careful about recognizing the proper forms that you can prove, and don't make these mistakes of trying to prove the converse or the inverse when asked to prove P implies Q. You can consider the contrapositive, but not the others. So that's it for this video. Thanks for listening.